In this section, we're going to take a look at conic sections in polar coordinates. The three conics are the ellipse, the hyperbola, and the parabola. Right? So here we start off with a sort of a theorem definition kind of thing. I don't know. It is a theorem, but in a way it defines, it gives us an alternate definition of what our conics are. So we begin with a fixed point. Let F be a fixed point, and it will not be moving. We call it F for focus. And let's let D be a fixed line. It's called the directrix. The directrix can be a line in any direction. However, for our purposes, we're going to be dealing with strictly horizontal or vertical lines. Hypothetically, they can be in any direction, though. Let D be a fixed line. And again, there's no restriction on what that line should be, but for us, it'll be vertical or horizontal. And this is called the directrix in the plane. Okay. And now let P be another point on the plane. Not necessarily the fixed point, not anything on the line, just some arbitrary point on the plane. Okay. And let E be the ratio of the distance between P and F and the distance between P and F, P and F, and the distance between P and D. You say, what's the distance from a point to a point? Okay, I know that. What do you mean by a distance between a point and a line? When we say the distance between a point and a line, we mean the shortest distance. Sure, you could start from one point and let's say I'm starting from this point right here and I want to get to this line. Well, there's lots of ways to get to that line, but we want the shortest one. Let E be the ratio of the distance between P and F and the distance between P and E. Here, this E is called the eccentricity. Oh, I'm sure I'm going to misspell this. Eccentricity, I believe. Oh, I got that right. Eccentricity, yay. The eccentricity. If you take every point of a given eccentricity, you get a conic. The collection of all points of common eccentricity form a conic. And not only do they form a conic depending on what the eccentricity is. So if the eccentricity is between 0 and 1, you get an ellipse. If you have your eccentricities exactly equal to 1, the points form a parabola. And if your eccentricity is greater than 1, the points form a hyperbola. Just like that. No? All right, so let's go ahead and illustrate this just very quickly to see what these things are here. It's difficult to illustrate the eccentricity without just making a conic. So here, let's just describe all of these other values here. So you have a plane. In fact, here it is. I'm going to draw it out right here. All right, so let's start off with a fixed point. Let's call that F, and that's your focus. Now you have some line. Okay, well, there's your line, and this is your directrix. There's D. Okay, so now let's take a point, and I'll just put it right over here between D and F. Okay? So here's a point, and I'll call that P. All right, now what we're going to do is we're going to measure. Let me not put it here because that'll make it a little hard to draw out the rest of this. So let's put it over here so that it's not directly in between the line and the focus. It's not wrong if it is. It just makes it harder for me to draw it. Okay, so let's call this the point P. All right, so now we're going to find the distance between P and F. Well, that's pretty simple. It's just a straight line distance. Okay, so here this distance is from P to F. All right, now we're also going to find the distance from P to the line D. Now remember, this point can be directed in any direction here. We can find the distance from here to here, here to here, here to here. But when we say distance, we mean the shortest distance. So right across, like this. So this distance from here is the distance from the line PD. Okay? And we're going to call that the line PD. And here, this is the line PF. The distance from here to here is the line PF. The eccentricity is simply the ratio of PF to PD. So E is given by the ratio PF, the measurement of that line, divided by the measurement of PD. And that's what we mean by eccentricity. Now let's say we measured that eccentricity. Let's say we actually measured this and measured this. And let's say we found the eccentricity was, I don't know, let's say it was 1/3. All right. So now, using that same focus and that same directrix, let's find every other point that also has that same eccentricity, right, of 1/3. If you do that, if you go through and find every point that has the same eccentricity of 1/3, it'll form an ellipse with the point P somewhere on it. If the eccentricity, on the other hand, was 1, and I found every point that had eccentricity 1, given that focus and that directrix, instead of forming an ellipse, it would have formed a parabola out this way. And if it had been the eccentricity greater than 1, it would have formed the hyperbola. It would have formed one of our 3 basic conics, and whatever conic it formed, the point P would have been somewhere on it. Well, it turns out that polar coordinates are really rather ideal for helping us describe conics. So here's another theorem. Let's say you have a polar equation. So the polar equation of the form, and this is going to look a little strange, but it's going to be written out in sort of a strange way so that we have positions to fill in certain values here in a moment. R is equal to E times D over 1, either plus or minus E times the cosine of theta, or R is equal to E times D over 1, either plus or minus E times the sine of theta, are going to give us a conic. The polar of the form give a conic where E is the eccentricity of the conic, and the number D, if you take its absolute value, it's the distance from the focus to the corresponding directrix. And the absolute value of D is the distance from the focus, which is found at the pole, and the directrix. All right. So this seems a bit convoluted, but an example clears this up really rather nicely. So here, let's take a polar equation and simply sketch the graph. So here we say sketch the graph of, let's say r is equal to 10 over 5 plus 4 sine of theta. Okay, just like that. All right, this does look a lot like one of these. R is equal to a constant over a constant plus or minus sine or cosine. Okay, in fact, it looks a lot like one of these. You have a constant on the numerator, you have a constant in the denominator, and here it's plus, not minus, something times the sine of theta. I will notice one thing, though. I will note one thing, and that's that this is not supposed to be any constant. It's specifically the number 1. Same thing here. Here, that's not the number 1. Okay, well, simple enough. Let's divide everything by 5. Whenever you have, what the theorem says, that whenever you have a polar equation, a conic in polar form, this constant here should always be the number 1. If it's not, well, it's simple enough to modify. We go ahead and divide everything by that number so that you end up with 1. So here this is the same as saying r is equal to 2 over 1 plus 4/5 times the sine of theta. Okay, now that that's the number 1, everything else should match up to what our equation looks like. And it does. Here you have a constant over 1 plus a number times that sine of theta. Once this is the number 1, this number right here is your eccentricity. And this number up here is your eccentricity times some other number d. So here this is going to be E times d. So that gives us all the information we really need. Note that here I have E is equal to 4 over 5. Here I know that E times d is equal to 2. Oh, but if I put those together, that just means that 4/5 times d is equal to 2. Right? E is 4/5 times d must equal to 2. That's my numerator. And so if I multiply now both sides by 5 over 4, here I get d is equal to 2 times 5 over 4, which will give me 5/2. Okay? So here I find that my eccentricity is 4/5 and my value of d is 5/2. Note that by our first theorem, which is going to serve largely as a definition for how our conics develop, if your eccentricity is less than 1 but greater than 0, you form an ellipse. If it's exactly 1, you form a parabola. Anything greater than 1, you form a hyperbola. And here our eccentricity is 4/5, which is most certainly between 0 and 1. So here, because our eccentricity is between 0 and 1, then that means we have an ellipse. So even before we start graphing any points, that number there tells us we have an ellipse. Remember, d tells you the distance from the focus, which is going to be at the pole, to the directrix. So here this is distance from pole, focus, to the directrix. All right, so now let's take a look and form a graph from this information. Oh, I guess before we look at the actual graph, there's one more thing to say. Here we know the distance from the pole, from the focus to the directrix, but of course distance can occur in any direction. So, okay, I know how far to go, but in which way? Again, here we're only dealing with cases where our directrix are either horizontal or vertical. Here, the plus or minus paired with the sine or the cosine are going to tell you which direction your directrix is going to go in. So the way it's going to look is if your equation looks like r equals ed over 1 plus e cosine of theta, or if your equation looks like ed over 1 minus e cosine of theta, in both of these cases, you're going to have a vertical directrix. If it's plus, it'll be to the right. If that's minus, it'll be to the left. So whatever your conic is, it doesn't really matter if it's a hyperbola, parabola, an ellipse, or really anything else. Well, I mean, I guess those are the only options, unless you kind of circle. Here, the directrix, the fact that there's a plus here and a cosine here tells you your directrix will be vertical and to the right. Here, the fact that there's a minus and a cosine tells you it's going to be vertical and to the left. And without much imagination, I think you see where the other ones are going to come from. If you have ed over 1 plus e sine of theta, or if you have r equals ed over 1 minus e sine of theta, well, here these make them vertical asymptotes. So these vertical directrix. So here these will be horizontal directrix. So the fact that this is sine of theta makes these directrix horizontal. Here the plus and the minus tell you which way, which direction. So here this will be positive, so it'll be a horizontal directrix above the pole. And over here we're going to have minus, so we'll have a horizontal directrix below the pole, just like that. Yeah? So cosine, left and right, sine, up and down. Yeah? Positive to the right, negative to the left, positive up, negative down. It kind of follows the same pattern that we usually see with pluses and minuses. Yeah. So now we have all the information that we need. In our case, we know the eccentricities between 0 and 1, so we know we're going to have an ellipse. We know that we have a directrix that is 5 halves of a unit away from that pole, away from that focus. And because of our equation here, that's going to be plus, and that's going to be sine. Okay, plus and sine. That means we're going to have a directrix that is above the pole. All right, so let's go ahead and draw that out. I'm going to draw this on a polar grid here. I know that my focus must be at my pole. That's always going to be the case for any of these. So here I'll label that as my focus. My focus. Okay. Now I know that my directrix will be horizontal and above the pole because again, plus sine right here, plus sine. Okay, and I know its distance. It's going to be 5 halves, 2.5 units above the pole. So I'm going to go from here, I'm going to go up 1, 2.5. So I'm going to have a horizontal line there that's going to serve as my directrix. Whenever you're graphing a conic, your conics will never cross their directrix. They're not asymptotes exactly because the graph won't follow them, but your graph will be bound by this. It won't ever cross these. And at least one part of your graph will cross in between the pole and the directrix. When I say at least one part of it, keep in mind that hyperbolas do go off in either direction, so you might have a part of it that doesn't cross in between. But whenever you graph, note that some point on your conic will be somewhere in between your pole and your directrix. Okay, so now we're just about done. At this point, we know that we have our pole. Along this line, we have our directrix. So now we just need a few points to connect our dots. We know it's going to be an ellipse, so there's not much more information that we need. Here, let's just go ahead and find a few points to go ahead and plot our graph. My suggestion is that you use the points in the simplest used directions. That is to say 0, pi, pi over 2, and 3 pi over 2. And when I say use those directions, I mean literally take those angles and plug them into your equation and see what happens. So let's go ahead and consider that as just a set of test points. Here I'm going to take r and theta. So here's my theta, here's my r. And I'm just going to use 0, pi over 2, pi, and 3 pi over 2. Okay, so let's see what happens. If I say 0 in here, well, sine of 0 is going to be 0 times 4/5 is still 0 plus 1 is going to be 1. So it's going to be 2 over 1. Okay, that's the number 2. So that means that if I'm facing in the direction of the angle 0, I'm going to go forward 2 steps. 1, 2. There we go, just like that. All right, let's try pi over 2. The sine of pi over 2 is 1. 1 times 4/5 is 4/5. So that's going to be 1 plus 4/5. Okay, that's going to be 9/5. And if I take 2 divided by 9/5, that's the same as 2 times 5/9. Divided by a fraction is the same as multiplying by the reciprocal. And that'll give me 10/9. Okay, so that means if I'm facing in the direction of pi over 2, if I'm facing straight up, that's just going to go up 1 and 1/9. So we're going to go up 1 and a little tiny bit more. And there we go. If we use pi, okay, sine of pi is equal to 0. 0 times anything is 0 plus 1. Okay, so it's going to be 2 over 1. And so if I'm facing in the direction of the angle pi, if I'm facing over here to the left, I'm going to go forward 2 steps, 1, 2. Okay. And finally, if I'm using 3 pi over 2, well, let's see, sine of 3 pi over 2 is, that's negative 1. Sine of 3 pi over 2 is negative 1. So 4/5 times negative 1, that's negative 4/5. And if I add 1, that's just going to be 1/5. Right? 1 minus 4/5, that's just 1/5. And if I take 2 and I divide it by 1/5, that's the same as multiplying by 5 over 1, which will give me 10. So this one has me going, if I'm facing in the direction of 3 pi over 2 down this way, I'm going to go forward 10 steps. Oh, and I wish I had a bigger graph here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's just say that's 10 out there. And there we go. We know it's going to be an ellipse. We know it's got to pass through those 4 points. So now we draw an ellipse. Try to actually draw an ellipse. Remember, ellipses are symmetrical and all that other fun stuff. If you are not going to draw it super well, that's fine. No one's going to mind too much about that. But every semester I'll have people take these 4 points and draw a diamond. It's not a diamond. At least try to draw an ellipse. If you're not going to do it very well, that's fine, but at least give it a try. It's not a diamond for sure. And there we go. This is a graph of our ellipse given by the equation r equals to 10 over 5 plus 4 sine of theta, or a little more simply, 2 over 1 plus 4/5 sine of theta. And there's our graph. So here, give this a try. See if you can graph the following. Sketch the graph of, let's try this one. R equals to 2 over 2 plus 3 cosine of theta. Okay. Remember to first set this equal to 1 right here. Make sure that you modify your equation so that this is equal to 1 right here. Then, using what's left, find your eccentricity, the distance and the direction to your directrix, and then plot just a few points to give you your conic. All right. Go ahead and pause the video, give it a try, and once you have a result, go ahead and unpause the video and we'll finish it off together. All right, so let's give that a try. Note we want this to be the number 1, so before anything else starts, we're going to divide everything by 2. So this will give us 1 over 1 plus 3/2 the cosine of the angle theta. Okay, so here that means your eccentricity is going to be 3/2. And so since that eccentricity is greater than 1, that means we're going to have a hyperbola. Okay, We know that the numerator is E times D, which is equal to 1. Well, then that suggests that 3 halves times D is equal to 1, right? E times D, that's got to equal to 1. But we know E is 3 halves, so 3 halves times D is equal to 1, which suggests D must equal to 2/3. So we know that we have a hyperbola with a focus at the pole and a directrix that's 2/3 of a step away from that pole, from that focus. Now, in which direction? Oh, well, this minus here, along with this cosine of theta here, tells us that our directrix will be vertical, and it'll be to the right of the pole. All right, and that should be all the information that we need to get started. All right, we have our focus that's at the pole, and we know that that's going to be right there. We have a directrix that's 2/3 of a step away from the pole, and it's going to be a vertical directrix that's to the right of the pole. Okay, so from here it's going to go to the right by 2/3 of a step, so not very much, not even all the way to 1. So right around here, I'm going to go ahead and exaggerate this a bit. I'm going to say this is 1 and this is 2. That way it'll show up a little better. So here we have our directrix is 2/3 of a step away, so 1/3, 2/3. There we go. Something like that. So now we have our pole, we have our directrix. We know that our hyperbola will pass between here somewhere. But remember, hyperbolas are going to have 2 branches, so you have one this way and one this way. Your conic does not ever cross its directrix. So now it's just a matter of plotting a few points. Here, let's take theta and use that to find r. Let's see here. And again, I'll just use the points that I'm familiar with. I'll use 0, pi over 2, pi, and 3 pi over 2. And we'll use that in this equation to find our values of r. You could use either one. It doesn't really matter. They are equivalent to each other. So here, if we plug in 0, the cosine of 0, let's go ahead and do it on this one. That way we don't have to deal with fractions as much. So here, 0, the cosine of 0 is 1. 1 times 3 is 3, plus 2 is 5. So 2 over 5. Okay, so 2/5. If you use pi over 2 right here, the cosine of pi over 2 is 0. And so 3 times 0 is still 0, plus 2 is just the number 2. So you have 2 over 2, which is the number 1. If you use pi, the cosine of pi is negative 1. So negative 1 times 3 is negative 3. And negative 3 plus 2 is negative 1. So I'm going to have a positive 2 over a negative 1, which is a negative 2. And finally, 3 pi over 2. Well, the cosine of 3 pi over 2 is 0. 0 times 3 is still 0, plus 2 is 2. So I'm going to have a 2 over a 2, which is 1. If you had done that with this equation, you would get the exact same answers. It really makes no difference. They are equal to each other, right? That's what equal means. So now we can just plot these points. If I'm facing in the direction of the angle 0, I'm going to go forward 2/5 of a step here. Oh, let's see. These are thirds, so that's 0.33, 0.66, right? Like that. 2/5 is going to be 0.4, so it's going to be just a little bit past 0.33. So right around there. Again, this is just a sketch. We're not going to pull out a ruler and make sure that it's exactly right down to the micron. That's close enough. If I'm facing in the direction of pi over 2, I'm facing straight up, well, then I'm going to go forward 1 step. So that's going to be 1/3, 2/3, 3/3, right up there. If I'm facing in the direction of pi, which means I'm facing to the left, I'm going to go backwards 2 steps. So even though I'm facing to the left, I'm going to go to the right. So that's going to go 1, 2 steps. And finally, if I'm facing in the direction of 3 pi over 2, then I'm going to go down 1 step. So that's going to be 1/3, 2/3, 3/3 right there. Now, if we didn't know any better, we might connect things in a strange fashion. But again, we know ahead of time that our graph must be a hyperbola. And so we know what hyperbolas look like. They have two branches. Here, this one's reasonably clear to map out. It's reasonably clear that this is one branch of my hyperbola. Now remember, my other branch of my hyperbola is going to be symmetric to this one. So whatever this one looks like, this one should look like the same in the opposite direction. And again, no one's going to pull out a ruler. I'm not going to trace these and say, oh, I'm sorry, they're not perfect mirror images. Close enough there. Note that even with a hyperbola, my graph does not cross my directrix. With an ellipse, it does not cross my directrix either. Because, of course, if it crossed my directrix, going back to our theorem and definition of eccentricity here, if the point crosses the directrix, then that means that there is a point which is got a distance of 0 away from the directrix since they intersect. But if the distance from a point to the directrix is 0, that means our eccentricity is undefined. So as long as we have a defined eccentricity, or in other words, as long as we have a conic, then the distance between any point on the conic and the directrix must be positive, right? It must be non-zero. Otherwise, the denominator of our eccentricity is undefined, and well, then we just broke everything. As our last problem, let's go ahead and do something just like this, but backwards. Here, let's go ahead and give an equation. Give the equation, and here we're doing it in polar. Give the equation of the conic described. Okay, let's take a hyperbola with eccentricity 3/2, and whose directrix is the line x equals to -1. Okay. This actually gives us everything that we need. All right, so note that if the directrix is equal to x equals to -1, a quick sketch of this shows us that we have, well, x equals, that's going to be a vertical line. And since it's -1, it's going to be a vertical line that's a step to the left of the origin on the xy plane. Or if we were measuring this as a set of polar coordinates, it would be one step to the left of the pole. All right? So you have all the information you need. You know your directrix, which gives you the location and the type of directrix that you have, the type being the direction here, and you have your eccentricity. We also know that every conic will look like either r equals to ED over 1 plus or minus E cosine of theta, or r is equal to ED over 1 plus or minus E times the sine of theta. So we fill in our template. We pick the appropriate one and fill in the appropriate values. So go ahead and pause the video and see if you can fill this out. Once you have a result, go ahead and unpause the video and we'll finish this one off together. All right, so let's take a look here. We know our directrix is going to be vertical and to the left. Oh, so because of this, we have a directrix that's vertical and to the left. Then we're going to use this version with minus. So we know our equation will look like r equals ED over 1 minus E cosine of theta. Right? The fact that this is a vertical directrix to the left, vertical to the left. And now we simply fill in our missing values here. We know E is equal to 3/2 rather. And since the directrix is x equals -1, that means that from the origin, or in the polar coordinate system from the pole, it's 1 unit away. So here we get that d is equal to 1. Remember, d is not the number, it's the distance, so it would be the absolute value thereof. Okay, so there's d is equal to 1. And so we end up with d is equal to 1, E is equal to 3/2, and so our equation, our hyperbola, is given by r equals 3/2 times 1 over 1 minus 3/2 cosine of the angle theta. This is correct, but it's never left this way. If you notice, every one of our starting equations starts off with everything as a whole number. Okay, so that's simple enough. The very last step here is let's go ahead and multiply top and bottom by 2, and that's just to clear out these denominators. Essentially, complex fractions are never a good way to leave anything. So let's multiply top and bottom by 2. That'll give us 3/2 times 2. Well, that's just the number 3. Over 1 times 2 is 2, minus 3/2 times 2 is just 3 cosine of the angle theta. Okay? And this is our result. This is a hyperbola with 3/2 eccentricity, a directrix that's one step away toward the left. It's a vertical line. And here we simply pop everything into this template and then simplify, because of course complex fractions are never a nice way to leave anything. So multiply gives you 3, distribute gives you 2 minus 3 cosine of theta, and that's your result. And that brings us to the end of this section.